Let's review constant pressure or coffee cup calorimetry. We assume that no heat is exchanged between the system and surroundings, only between system components. So the heat gained is equal to the opposite of the heat lost, or the heat lost is equal to the opposite of the heat gained. Either form of this equation is perfectly good. We recall the two forms of the equation whenever heat is being transferred, either within a given state of matter, in which case the delta T form, that is the one on the left, is applicable, or when there's a state of matter transition, we use the form on the right, where we have to choose the positive or negative sign, and then we have to know, is the heat of fusion applicable or the heat of vaporization. We would use the heat of fusion if we're doing a solid-liquid phase transition. We would use the heat of vaporization if we're doing a liquid-gas transition. This example involves a reaction in solution and the enthalpy change that accompanies that. When 50 mils of 0.1 molar silver nitrate and 50 mils of 0.1 molar HCl are mixed in a coffee cup calorimeter, the mixture's temperature increases from 22.30 degrees Celsius to 23.11 degrees Celsius. Calculate the enthalpy change for the reaction per mole of silver nitrate. These are our two reactants. If we put them together, we're going to get a silver chloride precipitate, an insoluble substance, in this double replacement reaction. Nicely, the coefficients for this equation are all 1. Since we have 50 mils, or 0.05 liters of each of these, and the concentrations are both 0.1 molar, whenever we're dealing with a reaction, we want to deal primarily with moles. Molarity is moles divided by liters, therefore moles is molarity times liters. So I've calculated that we have 0.005 moles of each reactant. We're going to have to make a few assumptions. Firstly, the specific heat of the mixture we're going to assume is very nearly the specific heat of water. And that's a very good assumption, because what do we have mostly in a couple of 0.1 molar solutions? Water. The specific heat of the mixture should be very close to simply the specific heat of water, which is 4.18 joules per gram degree Celsius. The other assumption we're going to make is that the mixture's mass is 100 grams, and that's because we have, if you look at the top of the screen, 50 milliliters of this solution and 50 milliliters of this very dilute solution, and we have memorized that the density of water is 1 gram per milliliter. So if we have 50 milliliters and another 50 milliliters of stuff that is almost completely water, then we have a total mass of 100 grams. The amount of heat that is exchanged or released in this reaction is going to be the mass, 100, multiplied by the specific heat of water, and then the temperature changes from 22.3 to 23.11 degrees Celsius, and we get a number like that, 338.58 joules. That is the enthalpy change for 0.005 moles of silver nitrate. Now we mention that because the last sentence in the problem says calculate the enthalpy change for the reaction per mole of silver nitrate. In other words, per 1 mole. We don't want the enthalpy change for 0.005 moles of silver nitrate. We want the enthalpy change per 1 mole. And if we do that and convert it into kilojoules, I've just converted it into kilojoules because it makes this number smaller and more palatable. 67.7 kilojoules per mole of silver nitrate. Now, is that a positive number or a negative number? What happened to the temperature of the mostly water? It went up, which means that energy was released, so the enthalpy change should be negative.